Let's say Kyle's example was example 1, so I'll go and do the next example, call it example 2, and here I'm going to use the term reparametrize. The reason I initially included this in my lecture notes is because I thought that I put a homework example like this, but turned out that I took it out. And I mentioned that already, so let me move on. Let's reparametrize the helix that I would have shown you if I gave you the first example. And it's cosine Ti plus sine Tj plus Tk with respect to, and you see me writing from this point on, instead of with respect to, I'll write WRT. So what do we want to reparametrize the helix with respect to the arc length measured from and we need to give an initial point, and we measure it from 1, 0, 0 in the direction of an increasing t, which is somewhat redundant because when we define the arc length function, we define it as the integral in the direction of increasing t. So let's see if we can make a sense out of this weird-looking example, because it's a little bit weird. Okay, first of all, we're going to say that the initial point 1, 0, 0 correspond to what value of t? Somebody said that, but go ahead. Correspond to what equals to 0? There you go. Say it in complete. Say a complete statement. So we're looking at t equals 0, and now remember how we took the derivative right here? Let's do the same thing. ds dt will be the magnitude of the derivative vector function r prime, and for the particular curve it would be the square root. Well, we take the derivative of the cosine, so it will be a negative sine t squared plus the derivative of the sine is cosine, so we have cosine squared, and the derivative of t is 1, so plus 1. And so what is this equals to? Without thinking too long. It's not 2, but square root of 2. I know. Ryan said square root of 2 initially. So what is s? Well, s now becomes s of t. And what we need to do, we integrate. And we integrate, remember, from 0 to t. So we go and we apply the definition of the arc length function here. So if you look here, it will be the integral of the magnitude of the derivative vector r prime of u du, and of course in this case we know it's simply a number, square root of 2, so it's the integral from 0 to t of square root of u square root of 2 du, or simply square root of 2 t, like so. Okay, so where is this business of reparametrization? Is expressing t in terms of s. That's what reparametrization means. Okay, so t, if s equals square root of 2 times t, well, t equal s divided by square root of 2. But we are not done. Okay? Because now we need to express everything in terms of s. So here's the Reparametrization. We take our curve defined by the vector r of t, but instead of r of t, we're going to use the composition. We're going to say it's r of s of t, like so. Or simply r of s. And we say this is equal to cosine, because t now is replaced by s over square root of 2. Then it will be cosine of s over square root of 2. No, the original r. It's not r prime, it's r. Plus sine of s divided by square root of 2 t. Actually, I need to close the This is in the I direction, so let me correct myself. So t times I plus sine of s divided by square root of 2 t j, and instead of tk we have s divided by square root of 2 k. Okay, what was the question? Yes, there is no t in there. Notice that initially I did not include it, but yeah, it's. Thank you so much, Kyle. You are sharp this morning. Why? You jump in too? Yeah. I heard several voices, that is true. So, good point. So, it's simply this I plus sine of s over square root of 2. It means that I need to look at my notes more often. There you go. All right, the next topic is curvature, but let me pause here or stop the recording.